everyone, welcome to today's video, and today I'm going to discuss about user material subroutine in ABAQUS CAE. Please remember to understand user material subroutine or this video you need to have some information about ABAQUS CAE, how to define a material model in ABAQUS CAE itself, and UMAT itself requires a lot of coding in Fortran and also requires expert knowledge in how ABAQUS really interacts with user material subroutine. And in this video I will introduce you to all those things. So I will start with what is a UMAT subroutine, then how to get started with using or writing a UMAT subroutine, then I will try to explain the structure of UMAT and what are the variables that are involved. Some are the inputs which are coming from ABAQUS CAE, while some are the outputs which have to be transferred or computed in your UMAT subroutine and then transferred back to ABAQUS CAE. So I will explain those, and finally a simple linear elastic isotropic model example. I will try to show you how you can implement that in a very simplistic way, and I'm not going to run any jobs today, but just to give you an idea how to implement and just to show you or give you the commands which you can use to run the software. Please note, every system is different, every operating system is different, and every version of ABAQUS and Fortran compiler is different, and I am not an expert to that. So I expect that you guys will have already ABAQUS and the Fortran compiler or Intel Fortran compiler or Intel Studio installed on your computer and working, rather than me explaining how to install, and I will not be able to do that. Sorry about that. Okay, so when you're doing an ABAQUS static analysis for any problem, let's say you have a simple model which is shown, if I can bring my pointer. So if you have this kind of problem where you have a bar which is pulled from one direction with in a displacement control test, and it is fixed from the other end, so you can model this as a 3D structure and divide them into finite elements, and then define the material properties. Again, if the material properties are linear elastic, then you need to define Young's modulus and Poisson's ratio if it's an isotropic material, and then you try to solve it and find out what are the stresses and strains in your object, right? Another simplistic way would be you can use a truss member, because it's an example of a truss element, so you can model it as a truss member as you shown here, and again you can do the same thing and you can estimate the stresses and everything in your truss model. This will save a lot of time. So again, depending on the problem, you can do that. Again, if you're not familiar with ABAQUS, I would suggest to go and look at ABAQUS courses which are there on my YouTube channel. Okay, so how does it work? So you match the part, you have defined the material properties which are linear elastic isotropic properties. So it will, based on the boundary condition, it will estimate a strain increment, which is change in displacement or change in the length over the original length, right? And it will have a, so based on the total time you are using and time increment size you are using, it will compute the increment in the strain depending on the increment of the displacement, and then it will take it to the material model which you have defined as a built-in model in ABAQUS. And it will, in this case it's a linear elastic model, so it will use sigma times E epsilon or whatever and compute the stresses and the Jacobian. So material model in a standard static analysis, you are supposed to calculate the stresses and Jacobian. I will come back to the Jacobian later on. And then once you have done that, you basically then have to solve for the balance equation. Again, this is done by ABAQUS itself, and so it's a global balance of the whole thing. Static, in this case it's a static equilibrium equation for Newton's law of motion, and then you check for the convergence. If it's converged, then you move to the next increment and it will come back with a new increment of strain depending on the boundary conditions, and do the same thing again and again until you reach to the final value of your displacement or the total step time. If it doesn't converge, it goes back and does the global iteration again, maybe reducing the time increments, etc., and do the same exercise again and keep on doing it unless it converges and move to the next increment. So this is how it works in a typical built-in model when you use. Now, if a model is not available in ABAQUS, then you are supposed to define the material model yourself, and ABAQUS gives you that flexibility. So what happens then is your built-in material model thing goes away. What you see basically is that your strain increment is now transferred to a UMAT. So you are supposed to write a UMAT subroutine. This UMAT subroutine should be written in such a way that it takes the material properties which are required. You can define that in the input file, and I will show you how. And then ABAQUS, based on the model, ABAQUS comes to the UMAT with a strain increment for each element. So how many number of elements you have for each element, it will compute the strain increment based on the boundary conditions and approximations. And then based on the material properties and the strain increments and the strain tensors, you are supposed to compute the stresses and Jacobian and any other variables which are required. Again, I will get back to that, what it means later on. So these are the things which comes to the UMAT as an input. So strain increment, which is coming from the model and boundary conditions, material properties, which are your input, current strain increment, as I told you, then the current strain tensor depending on the increments, and the previous stress tensor, and if there are any history variables, then they also come here from the previous increment. Here you will calculate stresses, the Jacobian, and the other state variables if they are there. What is Jacobian? Jacobian is nothing else but the partial derivative of the stress increment over with respect to the strain increment. And so this is your Jacobian. Again, if you go back to your basic continuum mechanics, you can see for small deformation theories and for linear elastic cases, you can approximate Jacobian with this kind of relationship. Okay, so this is what you have to do. You have to write a subroutine which can take all these inputs from ABAQUS when ABAQUS calls for each element, and it should update the stresses and the Jacobian or any other variable which are required for the later on for the next increment. And then the whole thing goes on as it was for the normal default model. So this block goes away and you are basically now in control of material model. That's the bottom line. Okay, so how does the UMAT really looks like? If you look at the UMAT syntax or UMAT block, then it starts with subroutine UMAT. It's a Fortran 77 compiler. The bold one here, these are the quantities which need to be calculated and updated. So remember, I told you stresses, any state variables which depend on the history like plastic strain, etc. You have to update those and store them in state variables so that you can use it for the next increment. This is DDS. DDE is the double derivative. This is the derivative of a stress increment with respect to the strain increment, and this is your Jacobian. So you need to define that. So these three things are the must if they are involved in your calculations. Other things involved are stress specific energies like plastic dissipation, etc. Again, you can look at ABAQUS documentation, and these can be used for post-processing or any other decision you want to make in the UMAT. If you're doing a thermomechanical analysis, then you also have to define the change of stress with respect to the temperature increments, etc. So these comes relevant when you are doing a thermomechanical analysis. So I will leave it for the time being. But these are the quantities which user has to define. All the other quantities you see here are passed in from either the previous steps or from the ABAQUS solver itself. So you don't have to really do anything about it, but you really have to take it and use it as you want for your calculation of stresses, state variables, and Jacobian. What is important here is when I told you about the properties you have to define. So in normal ABAQUS file, when you are using a default material model, the syntax in the input file will look like this, that it says static material, then the name of the material, and then you say elastic, and then you give the elastic constants, right? So then it means it's a default model. If you want to use, let's say, a linear elastic model with a UMAT, then you don't use the elastic, but you say static user material, and then you define how many constants are involved, and then you give the values. Again, ABAQUS doesn't know what these values are in default, because these will then be allocated or defined in your user material subroutine. So here you see props, and n props are these properties here. So in this case, we have two properties, so n props will be 2, and the props 1 and props 2 will be, prop 1 will be this, and prop 2 will be this quantity when ABAQUS reads the input file. Okay, then the other thing is the state variable. As I told you, you have to define the state variable, but again, you have to define how many state variables are involved. So you can have 6 components of plastic strains, or maybe some thermal components, or something else is there. So this n state variable will tell the UMAT and ABAQUS how many state variables are there, and how you tell this or how you define this is based on this statement here, which is static depth-var, and if you give a value of 1, this means there is one state variable involved in this calculation, and this means n state v is 1, so this means there will be one dimensional array for n state 1. If you look at different things, for example, how many components of stresses are there, state variables are there, and so on. So for that, Abacus defines their arrays. So for example, stresses are stored as one-dimensional array, as you see here, with n-tens. And what is n-ten? So that's what I'm gonna explain now. So stresses are stored as vectors, I told you. So for example, if you are working in a 3D space in a normal stress analysis or continuum mechanics approach, your stress tensor will be 3x3 matrix. In this case, Abacus stores it as a 6x1 vector. So you will have 6 component of stresses, and these are basically sigma 1 1 2 2 3 3 1 2 1 3 and 2 3. So this will be as stress 1, stress 2, stress 3, stress 4, and so on. So in this case, you can see for a 3D case, you will have 6 number of n-tens, and which is equal to the number of direct components plus the shear components. And you can see you have 3 direct components and 3 shear components. So that's why you have 6 here, and you will have 6 component of stresses. So in this definition here, wherever you see n-tens, this means you have, for a 3D case, you will have 6 components. Similarly, for n-tens and n-stat variable, I already told you this is defined based on the depth variable in the input file. So number, depending on that number, it will say that how many state variables are there. Again, you see this Jacobian, which is the partial derivative of the stress increment with respect to the strain increment, is 6x6 because n-tens is 6 and 6 in a 3D case, and so on. So you can see all these, how these really arrays are stored when you are defining or calculating any of those quantities. So if you move from a 3D case to a 2D case or 2.5D case in strict sense, then plane strain case or axisymmetric elements, you have n-tens equals to 4. Again, you can look at the Abacus documentation for more detail. So this means your stress will have 1, 2, 3, and 4 components, and similarly your Jacobian will have 4x4 matrix sort of thing. There are some other variables which you can use, like d strain is the strain increment, strain is the total strain, time has again array of 2. So time 0 is basically the time, step time, and type 1 is the total time if you have multiple steps. So it will can also store the total time. D time is the time increment, temperature is the total temperature, d temp is the total temperature increment, and so on. So again, all these variables are explained in Abacus documentation, so you can have a look if you want to use any one of those. What you have to do is, you don't have to change anything, you just copy the whole block, and this is the area where you define or write a code to calculate, as I told you, the Jacobian, the stresses, or any other quantities which are relevant for your analysis from this bold section. Okay, so let's move on to the UMAT and see if how we can implement this very simple linear elastic material behavior, which is for an isotropic case. So in the for that case, we can use a Hooke's law, since it's a linear elastic material, where sigma, which is the stress tensor, is given by the elasticity tensor times the strain tensor, and your stress tensor in this case is 6x1 times the 6x6 elasticity tensor times the strain tensor, which is given here. And what you have to do now is, you, as in an Abacus, I told you Abacus will call UMAT with the strain tensors and increments, d strains with 6 components. You have to define the Jacobian, which is this one, because this is the, if you take the if you say that this is the strain increment, this is the stress increment, the relationship remains the same. And if you take the derivative of this delta sigma with respect to epsilon, this whole thing will go away and you will end up with this. So that's your Jacobian in this case. In a linear elastic case, it's a simplistic problem. So this is our DDS, DDE, and this is 1 by 1 comma 1, 1 comma 2, and this is, and so on. So 2 comma 2, 3 comma 2, and so on, 6 comma 6. So it's a 6x6 matrix. So we need to compute this and define this, and also we need to compute the stresses based on the strain increment, which is d strain 1 to d strain 6. So that's what we're going to do in our code now in a very simplistic way. Okay, so this is the code, and here I'm gonna, this yellow highlighted section, I'm gonna define that. So I'm gonna remove all the other stuff and I will just show you this part now from now on. So your input file, you need to keep the structure like this, that you have 2 constants, so 2 properties. Prop 1 is this, prop 2 is this, and you have 1 state variable. In this case, state variable is irrelevant because it's an elastic problem, so we don't have any variable which will be required in the future, so we are not going to store, but you can store any variable if you want. So first thing is, when Abacus calls the UMAT, it goes to the input file and it reads these 2 constants, and these are props 1 and props 2. So these comes directly in the UMAT, and you can assign them as E and nu depending on how you have defined these constants in your input file. So I'm just calling prop 1 as E and prop2 as a Poisson's ratio. The second thing I do is now I basically have, if you remember, and if I can see here, so basically what is happening here is, if you go back to this slide here, so I have this term which is computed several times and will be multiplied with several things every term here. So I'm going to compute this separately and also some of these terms separately, and that's what I'm doing here. So this is E over 1 plus nu 1 minus 2 nu. This is the term which is out of the parenthesis, 1 plus nu over 1 minus nu, and then I'm also computing these terms. So I call this as term 1, term 2, and this is term 3. So that's what you see here, term 1, term 2, and term 3. Also what I do now is I assign DDS, DDE, which is the Jacobian, to be 0. So all members from, this is a nested loop, you see 1 to n tens, n tens is 6 in this case. If it's a 2D case, it will automatically become 4 for plane strain or axisymmetric case. So this will become 6 by 6, and I am assigning everything to be 0 because you see a lot of terms in this matrix are 0. So I basically I'm making everything first 0, and now I'm only going to compute the ones which are non-zero in this matrix to save my time. So that's what I have done here. So I make everything 0, and then I go to the next loop here, and based on these relationship I will compute each one of them. So you see 1 1, 2 2, and 3 3 are the same. So I will compute term 1 times 1 minus nu, and if you remember, 1 minus nu term 2 was 1 minus nu here. So 1 minus nu was the term 2. So term 1 times term 2 will become D in this DSDDE 1 1, 2 2, and 3 3, and they are the same. So you see here. Now I can also compute the 3 3, 4 4, and 4 4, 5 5, and 6 6, and that's the term 1 times this is term 3 if you remember in that code, and that's what I've done, term 1 times term 3, and I compute that here. So I'm just computing only the non-zero ones because I have made the rest of all these things as 0 here, and then I do the same for the rest of the off diagonal terms. So it will be nu times this, so term 1 times nu, and so on. So these are all term 1 times nu. So I have 1 2 3 4 5 6 additional values here. So this way I have computed the DS DDE, which is based on the linear elastic tensor. Okay, so that's what I have done here, and now what I do is I need to update the stresses. So what I can do is I will always do everything in an incremental form, because for later cases when we will be doing elastic plastic analysis or viscoelastic analysis, everything will be time dependent and also will depend on the strain increment. So what I do when UMAT is called, it calls the stress one, and stress basically stores the previous stress in the previous increment, right, converge increment. So what it does is it uses that increment and it updates the new one based on the new strain increment times the Jacobian, right? So that's what I have done here, because your stress increment, which will be current stress minus the previous stress, will be equal to Jacobian times the strain increment, right? So I just add the previous stress into the current stress increment and I get the total stress, and I update the stress this way. So now I have defined two things. I have calculated the updated stress and I have calculated the Jacobian. And once I have done that, my UMAT is ready with all the codes and everything, and I just go and I will create an input file. Again, you can look at my videos on how to create a simple uni-axial test example. So you just, with one element, define the material constant and material constants as this in the input file, and then you can use this command in ABAQUS command prompt to run the ABAQUS with a user material subroutine. So it's ABAQUS job equals to the name of the input file, user type equals to the name of the user material subroutine. I always use double precision to avoid any issues with the numbers, and then interactive mode. This will give you on the screen in the command prompt if there are any compilation issues or some other errors which you get during the run. So once you have run that, you will get an ODB file and you can post process the data as you do it for a normal ABAQUS file. So I hope this makes sense. Again, when you have made a UMAT, remember that it's a very specific thing, and it requires a lot of expertise to write UMAT, and you need to verify and test your UMAT for all possible cases. So the best approach normally is to use a one element model. So create a one element cube, apply the uni-axial case, and do a lot of different types of displacement control tests. So you prescribe a displacement boundary condition and do maybe a uniaxial test, then maybe uniaxial in the oblique direction, finite rotations, finite shear. So try to deform in all possible ways and see your UMAT behaves the same as it should be for a normal linear elastic model in ABAQUS, because a linear elastic model which is already available in ABAQUS, so both of them should give you the results. Also you have to do the same with the force model. So you, instead of applying a displacement, you can apply a force and do the same, repeat the same test and see if you get the same results as in the default ABAQUS model. If there are no default models available, then look for some analytical solutions for the theory which you have implemented in the UMAT and see if you can verify and validate your UMAT with those for different types of loading, because it is very important that your UMAT works for all sorts of cases and you have taken care of all the glitches and all the issues which you can come across in the UMAT. So I hope this makes sense, and you have now learned how to implement a simple linear elastic model in ABAQUS using a UMAT in a static analysis. And if you want to learn something more on UMAT, then please comment below, and please don't forget to like the video as well, and I will come up with that video. I will also make a video on how to use or implement the same linear elastic model in UMAT in near future, and so hopefully you will like that as well. So thank you very much and good luck with everything.